Okay, let's talk about rotational energy and the ground state probability for a molecule. So we've got a question here. The rotational energy of a molecule, when it's in an angular momentum state that we label as J, is given by this formula, Ej equals h bar squared divided by 2I times J plus 1. Here I represents the moment of inertia of the molecule. The question asks for the probability that this molecule will be in its ground state at a temperature T, where we are given that kBT is much greater than h bar squared over 2. Let's jump into the solution. We already know that the rotational energy for a state J is given by Ej equals h bar squared over 2I times J plus 1. An important point here is that each rotational state J actually has a degeneracy, meaning there are multiple ways to achieve that energy level. The degeneracy, which we call Gj, is equal to 2J plus 1. First step in figuring out the probability of being in the ground state is to actually identify what the ground state is. The ground state corresponds to the lowest possible angular momentum state, which is where J equals 0. Now let's calculate the energy of this ground state. We just plug J equals 0 into our energy formula. ESO equals h bar squared over 2I times 0 plus 1, which simply equals 0. So the ground state energy is 0. And what's the degeneracy of this ground state? We plug J equals 0 into the degeneracy formula. G0 equals 2 times 0 plus 1, which equals 1. The ground state is non-degenerate. Next, we need to recall the Boltzmann distribution. This distribution tells us the probability of a molecule being in a specific state J at a temperature T. The probability Pj is given by Gj times e to the power of minus Ej over kBt, all divided by z. Here z is what we call the rotational partition function. Let's calculate this rotational partition function z. The partition function is essentially a sum over all possible states. So z is the sum from j equals 0 to infinity of gj times e to the power of minus ej over kbp. Now we substitute in the expressions for gj and ej that we know. Z equals the sum from j equals 0 to infinity of 2j plus 1 times e to the power of minus h bar squared over 2I times j plus. Now, applying the high temperature approximation, the condition kBT is much greater than h bar squared over 2. I tells us the thermal energy is much larger than the energy difference between rotational levels. When this condition is met, we can approximate the sum in the partition function as an integral. Let's define b as h bar squared over 2I for simplicity. The condition is then kBT is much greater than b. Our partition function given by the sum can be approximated by an integral under this high temperature condition. To convert the sum to an integral, we use a substitution. Let x equal j times j plus 1. This means dx becomes 2j plus 1 dj. The limits of integration follow. When j is 0, x is 0, and as j goes to infinity, x also goes to infinity. So the partition function z can be approximated by the integral shown integrating from 0 to infinity. So the partition function z can be approximated by the infinity. Let's continue applying this high temperature approximation by evaluating the integral. The integral of e to the power of minus ax dx from 0 to infinity is typically evaluated as minus 1 over a times e to the power of minus ax evaluated from 0 to infinity. Here our r is b over kBt. So z is approximately equal to minus kBt over b times e to the power of minus bx over kBt evaluated from 0 to infinity. This simplifies to minus kBt over b times e to the power of minus infinity minus e to the power of 0. That becomes minus kBt over b times 0 minus 1, which is simply kBt over b. Now we substitute back our definition of b, which was h bar squared over 2I. So z is approximately equal to kBt divided by h bar squared over 2I, which simplifies to 2I kBt over h bar squared. Now that we have the rotational partition function z in the high temperature limit, we can calculate the probability of the molecule being in its ground state, which is j equals 0. We'll call this P0. Using the Boltzmann distribution formula for j equals 0, B0 equals G0 times e to the power of minus E0 over kBt, all divided by z. Let's substitute in the values we found for the ground state. G0 is 1, E0 is 0, and we just calculated z as 2I kBt over h bar squared. So P0 equals 1 times e to the power of minus 0 over kBt, all divided by 2I kBt over h bar squared. This simplifies to 1 divided by 2I kBt over h bar squared. Finally, we get P0 equals h bar squared divided by 2I kBt. So the calculated probability for the molecule to be in its ground state at this high temperature is P0 equals h bar squared over 2I kBt. Let's compare this result with the options we were given. Option 1 is 3 over 2 times h bar squared over I kBt. Option 2 is 2 over 3 times h bar squared over I kBt. Option 3 is 1 over 2 times h bar squared over I kBt. And option 4 is h bar squared over IKVT. Our calculated probability h bar squared over 2 IKVT can be written as 1 over 2 times h bar squared over IKVT. This exactly matches option number 3. Therefore, the final answer is option number 3.